made by Brian Mackley, and Kagoshima University film made by Toshiya Doi, and DC Measurements, Los Alamos folks, Nestor Haberkorn and Leonardo Civale. And RF Measurements, Sami already mentioned about the system, but there's a postdoc named Jichen Go, and he is doing the measurements with Sami. And there's a lot more contributors, but they're less contributed to this, so I put their names at the end of the presentation. Okay, the outline of my talk, it's kind of duplicate of the previous talks, but introduction and also DC measurements and results, and RF measurement and results. And there are some issues and concerns, and I'll summarize and mention some future plans. Okay, introduction. Okay, our final goal is to achieve more than 50 megavolts per meter accelerated gradient, and hopefully about 100 megavolts per meter at least. And that means that if niobium technology that we're using now is limited, fundamentally limited by around 20 millitesla, that means about 50 megavolts per meter. But there are several ideas to, like tricks to increase it that have been considered and been done. There are some possibilities. The first one is to tweak the shape of the cavity. As you can see, this is a standard shape, and then, can you see? Oh, it's lost the light. Okay, so if you change the shape from this standard shape to like what we call like lotus shape and reentrant shape, you can change the parameter of B peak, the ratio of B peak to accelerated gradient door. So that way you can effectively reduce the field, magnetic field. That way you can increase the achievable accelerated gradient. And it's been very successful, and there is something I don't know about this, is not really just tweaking this ratio doesn't seem to be consistent with just this about 10% of increase. We've got more than 10%. I don't know the reason, but anyway, this is one of the possibilities to increase the field, accelerated gradient. And another possibility is FEMLab is working on this, but usually these superconducting cavities are operated in standing wave mode, but according to them, if you change the mode to traveling mode, and then that could increase the transit time factor, and then it could increase the accelerated gradient, or the energy gain per unit length could be increased by like 40%. That's what they're saying, and they're working on that. And the last thing I'm going to talk about mostly here is this coding. And already it's MgB2. This is about MgB2, and MgB2 is, in my mind, it's one of the most promising candidate to increase the cavity. And Alex's theory suggests that it could significantly increase the surface magnetic field by making multilayer films. Okay. Roland already told you about this, but so this type 2 superconductor has two critical fields, and RF field is between HC1 and HC2, somewhere between here, and then depending on the copper, as you saw, the RF critical field is either higher of HC or lower of HC. And this is just a curve that's derived from this Rx equation here. At the extreme limit of this, the thickness is thinner than the penetration depth, and my assumption is the coherence length is 5 nanometer and penetration depth is 140 nanometer. If you put this in this equation, you get this curve. And depending on the penetration depth, this is not valid. If it's thinner film, it's not valid. As you can see, if it should be like 140 nanometer or thicker to make this valid. Oh, yes, thank you. Okay, this is just a simple sample of this effect. We're combining with this better this ratio B peak over accelerating gradient, and then assuming that on niobium surface it can sustain like 170 millitesla, and then if you add one more layer, and then at the very surface of this layer could be like 355 millitesla with that from the curve you saw. That means about, with this ratio, about 100 megavolts per meter accelerated gradient, even one layer. If you add more layer, of course, it gets higher and higher. And then eventually probably limited by the electric field emission or something like that, about like surface field of more than 200 megavolts per meter. Okay. So this is the concept of increasing the surface field. Okay, let me talk about DC measurements and results. Before going to the measurements, I'll tell you a little bit about these two methods. The samples were prepared with two methods, as I said. This one has been already explained by two previous speakers. And one thing may not have been mentioned was this heater is at about 550 degrees C. And the other one was in Japan, in Kagoshima. Kagoshima University has this system. It's two e-beam gun, two sources, magnesium and boron, and both vaporized with EV gun, and then it's co-evaporation. It's a true co-evaporation. This is a sort of a sequential co-evaporation, and then since it's true co-evaporation, the reaction is faster, and then the temperature. The advantage of this system is temperature could be as low as like 250 C, and the magnesium, according to Xiaoxin's the diagram, the lower the temperature, the magnesium concentration could be lower. So this system is sort of a low temperature coating system. Okay, this is a DC measurement concept. We use this quantum design magnetic property measurement system, MPMS SQUID, is used. And with this system, it's a simple formula. The total magnetic moment with this field, applied field, is written like this, and V is the volume of the sample, and D is called demagnetization factor. And this number, 1 minus D, becomes, if the field is parallel, is about 1, and then if its field is perpendicular, it's about 0. We can, because it becomes around 0, it becomes like infinity, so we cannot measure this. and this dMdH is called Meissner's slope, and then sorry, I forgot. This formula is only valid for the Meissner state, and well, Alex said you cannot believe HC1 measurement, but our experts did this measurement, and then what we did was, this is a field, applied field, and if the sample is tilted by about theta, and then this is combined magnetization formula, and then according to our guys, they say alignment is 0.1 degrees or better is needed. It's much relaxed than Clea said. Clea said like 0.001 degree or something. But okay. Well, they think this is good enough. Okay, so in this presentation, I define HC1 as the point where this is Meissner slope, where this data starts to deviate from this slope. That's what I define as HC1. But I'll show you some other definitions later. But anyway, if we define HC1 as such, then this is a sample of one of the samples that we measured. As you can see, at lower temperature, it starts to deviate at higher field. But for example, 25K, it's this one. It gets much lower field when it's deviate from the Meissner slope. So from that, we get this kind of data. Okay, as a reference, we measured a niobium rod, bulk niobium. This is consistent with our cavity testing, for example. For example, it's about 5 Kelvin. It's about 1,450 Elsted. And our system currently, we have measured down to only about 4.5 Kelvin. And this graph shows STI film. And the STI film has TC of about 39 Kelvin. And this error bar corresponds to, well, sometimes it's difficult to see, to say just one point when to say where it starts to deviate. So that's the uncertainty. And it goes like this. And then I added this later because those guys who measured this data didn't add this. So I thought before measuring at 4.5 Kelvin, I thought it will saturate like this, but it didn't saturate and it went up. So, and as you can see, if you define HC1 as such as what I said, then the HC1 of MgB2 is about 500 Elsted larger than niobium, bulk niobium, which is very good.